Hello. Unit 4 deals with the periodic trends of the elements, and in this video, I want to tackle the next couple of trends, which are atomic radii and ionic radii. Before I tackle those two trends, the first trend that I did talk about was effective nuclear charge. Effective nuclear charge trend, and that was in video 04K50. These are the next two trends, atomic radii and ionic radii. For atomic radii, it's pretty simple, at least going down a group. Before I talk about that, when you talk about an atomic radii, basically you have an atom, and the electrons are found within this volume 90% of the time. We learned that with Schrodinger's wave equations and definitions of orbitals. And simply the radii or the radius is just this distance right here, r. Now, if you have two atoms close together but not bonded, then the distance between the two nuclei are two of these, 2r. But right now, that's not the important part. The important part is what are the trends as we go either down a group or across a period. And the easier of the two is going down a group. We have our little cartoon of our periodic table. And as we go down a group, the atomic radii gets bigger. The atom gets bigger. I'll write that formally. As you go down a group, or a group is the same thing as saying a column, atomic radii increases. And that should be obvious. Your atom is getting bigger, but you want to think of it as your n value is getting larger, or your shell value. Increase n, or you could call this the shell. You think of an atom, and you have energy levels. And as you get further away from the nuclei, or the nucleus, you have n equals 1, 2, 3, etc. For instance, as you look at the periodic table, this southwest corner, that's francium. Okay, and n equals 7. Way up here is hydrogen, and n equals 1. Definitely francium is much bigger than hydrogen. So that's our first trend. The next one is a little bit counterintuitive. Let me draw us our little periodic table again. And let's read the periodic table from left to right. In this case, as you go from left to right in a period, the names of the rows are called periods. The atomic radii decreases. And that may be a little bit surprising for some of us. So I'll put exclamation points. That's surprising because the radii decreases even though the atomic number and the atomic mass increases. Even though, actually, let's not worry about the atomic number. The average atomic mass increases. You see the discrepancy there. It's getting heavier, more massive, but the radii is actually decreasing. It's getting smaller. The size is getting smaller. Why is that the case? That is the case because your n value stays the same. or the shell stays the same. Stays constant while what? While the number of protons increases as you go from left to right. As the number of protons increases, the pulling power, the attractive power, gets stronger. Now this n value, it's a general distance from the, it reflects the general distance from the nucleus. So when I say that all atoms or all elements in a row have the same n value, that's true, and they have the approximate distance. The outer electrons have the approximate distance from the nuclei, but still, that approximate distance is getting shorter and shorter as you go across the periodic table. For instance, let me pick up two examples or two elements. Lithium has 3 protons, okay, but the n value is still, from the periodic table, it's still 2. It's in the second row. So n value equals 2. But if we stay in the same period and pick up something like oxygen, oxygen has 8 protons. It has a better pulling power, but the shell doesn't increase. So in general, again, those electrons, whether they're the valence of lithium, electrons of lithium, or the valence electrons of oxygen, they occur approximately in this space here, n equals 2. But since we have more protons for oxygen, it's getting pulled in a little bit closer. Let me write out actually all the elements in period 2, and let's plug in some numbers into this table. And we'll go all the way to neon, the noble gas in period 2. The number of electrons. The number of electrons are 3, 4, 5, 6, 7, 8, 9, 10. But the n value is still 2 for all of them. 2, 2, 2, 2. The z value. Do you remember what the z value is? The z is the number of protons, the atomic number, and that's the same as the number of electrons. The pulling power as you get larger in z gets stronger, and the radii thus becomes smaller. And here are the real numbers. Lithium, 152 picometers. Picometers is simply just do times 10 to the minus 10 meters. Okay, and then you could put this into proper scientific notation. What would that be? 1.52. So I always get this incorrect. I moved it here, so I moved it 10 to the minus 9, 10 to the minus 8 meters. Are those two equivalent? Yes, because if I moved it to the right, I would have to make this 10 to the minus 11. So these two are equivalent. For beryllium, 112. Let's go to the other side, down to 72, and then neon is 70 picometers. Picometers. Okay, so again, this trend, now that the one that I've drawn, as you go from left to right, the atomic radii decreases. Let us combine those two trends for atomic radii, increasing, going down, and in this case, let's say increasing going to the left. Okay, I like to draw my diagonal arrow showing how the trend increases. Okay, so here's my picture, and what do we say? It increases as you go definitely down the group, and it decreases as you go across. So, which element would have the biggest atomic radii? Francium. When you take a look at the main uh, body of elements, and the trend goes this way. That arrow indicates increasing. Give me a second. Yes, increasing, because here the elements on the left are larger than the elements on the right within the same period. Increasing atomic radii. You don't really want to memorize a trend. You want to be able to explain why. For instance, why is fluorine smaller than beryllium, even though fluorine is more massive? It has a higher average atomic mass. Okay, that's the discrepancy, or that's the surprising part. I think I did draw this. So it goes to the southwest for increasing atomic radii. Let me double check that. So my cover slide shows 3 trends, and here's the atomic radii going to the southwest, the bottom left. That is the biggest atom within the main group of atoms. Okay, we're not talking about the actinides and the lanthanides, the 2 rows underneath the periodic table. Okay. Then the second trend, it's not really a trend, but you have to know what happens when you make these elements or these atoms charged, either gain an electron or lose an electron, and what happens to their radii in comparison to the neutral atom. So let me show you that. This first page was atomic radii. The second page will be ionic radii. This will take some practice. If you're like me and you have 2 choices, increase or decrease, bigger or smaller, I myself get nervous and I sometimes pick the opposite answer. So I would want to practice before an exam. The next trend is ionic radii. And the way I want to teach this is, let me give you an actual problem. And that problem is, which is bigger? An atom of potassium, or if we ionize it to K+, which of those 2 are bigger? Okay. And also, which is bigger out of these 2? Bromine and Br minus. Bromine Br minus. So for this one, what do? We lost an electron. And for this one, we gained an electron. How atoms ionize into their common ion, that was a topic in a different video or a different section. What I'm concerned about here is the size. Let's take a look at potassium. If we look on the periodic table, potassium has 19 protons, okay? And it's in the n equals 4. 1, 2, 3, 4. Right now, I don't have a clear idea of what the answer is. So I'm going to jot down some data. K, when it's neutral, has 19 protons and 19 electrons because it's neutral. And n equals 4. If I go to K+, it's potassium, so I still have 19 protons. I still have the pull, right? The attractiveness of a plus 19 charge. Let's not worry about figuring out the effective nuclear charge. The nuclear charge, ignoring all the other electrons, is 19, plus 19. But I lost an electron, 18 electrons. and I'm still within the same shell, the same general size. But I want to know, do we get a little bit smaller or do we get a little bit bigger? Well, look at this. Here we have 19 protons pulling 19 electrons. But in this case, we only have to pull 18 electrons. So the pull per electron is larger in this case. The pull, or the attractive force per electron, is larger. If that's true, then the radii becomes smaller because you're pulling those valence electrons closer. Our conclusion should be that this is bigger and this is smaller. The radii, let me do this in green. The real data is this. The potassium neutral has a radii of 227 picometers, whereas the ion is 130, I can't read my handwriting, 138 picometers. Okay? And that was our prediction based on this idea that we have the same number of protons pulling the electrons closer, but for this one, since we only have 18 electrons, the pull per electron is larger. Can you imagine what happens with bromine? Let's do the same analysis. Bromine is also with an n equals 4, and it has 35 protons. And 35 electrons, and n equals 4. I like to put the shell just to remind myself that these are all kind of close together in terms of the orbit, the distance from the nucleus, but it's going to be modulated a little bit by the ratio of protons and electrons. Because bromine minus still has an n equals 4. It still has 35 protons, but because we're negative, we added an electron. Okay, we ionized it. So that's 36 electrons. Still n equals 4. Okay. Okie dokie. So how do we do the analysis here? Initially, you have 35 protons pulling 35 electrons, and then you have some radii, some known radii. When you add an electron, you see now the pull per electron is smaller because we have more electrons. Pull per electron is smaller, or you could even call it weaker. You would imagine that you would predict that this is bigger, okay? Because we added an electron, but we didn't add another proton to balance it out. But I would think of it this way. Compare to the bromine that's neutral, bromine that's negative, the pull per electron is smaller. And the data bears it out. This is 114 picometers. And, okay, I almost got nervous there. The pull is smaller, therefore the radii is bigger because you're not pulling those electrons harder towards the nucleus. That's why this number should be larger, because the pull is less than in the neutral atom. So depending on whether you make, these are called cations. If you become a positively charged ion, and when you become a negatively charged ion, it's called an anion. And I'm going to circle the bigger ones. So between these two versus, this is the bigger, and between Br neutral and Br minus, the ion is bigger. The ion is bigger. You want to do this analysis on a case-by-case basis, but the trend usually is, well, I actually can't think of an exception. Cations become smaller from the parent, and the anions become bigger from the parent. All right, that is atomic radii and ionic radii. The next two trends in later videos, and these are the last two trends, is how easy is it to lose an electron, and that is called ionization energy, or we're going to measure the ionization energy, or to gain an electron. And that trend is usually attributed to, it's called electron affinity, right? To the affinity to gain an electron. Those two, for most classes and textbooks, are the last two trends, and I'll talk about that in a different video.